In this video here, we're going to take a look at Bezout's identity. Now, by using the Euclidean algorithm and back substitution, we can write the greatest common divisor of two numbers as a linear combination of those two numbers. And Bezout's identity states that if a and b are non-zero integers, then there exist integers x and y such that the greatest common divisor, the GCD, of a and b is equal to ax plus by. And before we work through an example here on Bezout's identity, you also need to be aware of the following. So for the first point here then, two integers a and b are co-prime if the greatest common divisor, or the GCD here, of a and b is equal to 1. Now, just a quick point here, this word co-prime, you might also see that referred to as relatively prime. They just mean the same thing, but certain, exam questions might use relatively prime as opposed to co-prime. Okay, but just a little point there to be aware of. And then for the second point here, the integers a and b are co-prime if and only if there exist integers x and y such that ax plus by is equal to 1. So in terms of an introduction here to Bezout's identity, we don't need much more than that. So I think the best way to really demonstrate Bezout's identity here is just work through a practice question together. So let's just get started then with this practice question. So let's just get started then with this practice question here. So if we just make a start then with part A here. So nice and straightforward then, all we want to do here is use the Euclidean algorithm to show that 41 and 14 are co-prime. Okay? So in that case then, 41 here. So 41 is equal to 14. Now, what I consider here then is how many times does 14 go into 41? Well, it goes in 2 times, so I get 14 times 2. What we now consider then is what is the remainder. I'll do 41 minus 28 here, which gives us 13. So my remainder then is 13. Okay? Now, as we can see then, our remainder here isn't 0. So in that case then, we need to continue with the algorithm. Okay? So nice and straightforward here, everything just shifts along. So the 14 here goes on the left-hand side. To get 14 is equal to, and now the 13 here shifts along. We get 13. So again, what I consider here is how many times does 13 go into 14? Well, nice and straightforward then, that goes in 1 time. I do 13 times 1 here. And again, nice and straightforward. You just get left with a remainder of 1. Okay? And again, what I can see here is my remainder is not 0. So again, that just tells us here that we need to continue with the process and the algorithm. Okay? So shifting everything along here, what I get then is 13 is equal to, so the 1 here shifts along. So how many times does 1 go into 13? Well, nice and straightforward, then it goes in 13 times. So we do 1 times 13. And as we can see then, we get left with a remainder of 0. Okay? So because we have a remainder of 0, the algorithm terminates here. And what that tells us then is the GCD. So let's just write this down underneath here. So the GCD then of our two numbers, 14 and 41. So 14 and 41 here is equal to 1. The last non-zero remainder. Okay? And because then the GCD here of our two numbers, 14 and 41, is equal to 1, what that tells us then is these two numbers are co-prime. Okay? Let's just make a point here of that then. So therefore, in that case then, 14 and 41 are co-prime. Okay? Are co-prime as required. Okay? So there we have it then. Nice and straightforward, hopefully. That gives us the solution to part A. Now, for the second part of this question here, then part B, well, it just says, hence find the integers a and b such that 41a plus 14b equals 1. Now, as soon as we see an equation of this form here, something that looks like this, right, that instantly suggests that we need to use Bezout's identity. Okay? So let me just start by writing down this equation here. So we've got 41a plus 14b is equal to 1. Okay? Now for Bezout's identity then, all we need to do here is work backwards, okay? So what we do then, and let me just do this in a different color just to make it clear, is we start at this line here, okay? The line where we obtained our GCD, okay? So going back to my original pen color here. Well, what I do then is I rearrange here, making our GCD the subject. Okay, so what I get here then is 1 is equal to 1 lot of 14. So 1 lot of 14 minus then 1 lot of 13. Okay, perfect. And what we do now is we keep going here backwards. So I now go to the next line here, which is our very first line within the Euclidean algorithm. Okay. And hopefully then what you can see here is we can rearrange and make 13 the subject. And what we can do then is substitute that into this line here. Okay. So if we make 13 the subject here then, so I'll just do it in a different color underneath here, just so you can see then. So 13 then is equal to 1 lot of 41 minus 2 lots of 14. Okay. And all I'm going to do here then, as we've just said, right, is just substitute this here into 13. Okay. So if I do that underneath, then what I get here is 1 is equal to 1 lot of 41 minus then, I get minus 1 lot of 13 here. So that's just minus then this here. So if I do it in a bracket, then what I get here is 1 lot of 41 minus 2 lots of 14. Okay, close those brackets like so. And if we just simplify here then, what would I actually get? Well, what I can do here is expand this bracket out, right? So I get 1 is equal to 1 lot of 41 minus then, so I get minus 1 lot of 41. So minus 1 lot of 41, like so. And then what I get here is minus 2 lots of 14. So just be very, very careful with the signs here. It is really easy to make a mistake then. So what I get here is plus 2 lots of 14. Okay. Now, if I just simplify here then, well, what do I have then? Well, I've got 1 lot of 41 minus 1 lot of 41. Oh, that should be 14 there. I made a mistake. Apologies. Let me go back. I was going to say something isn't working out here. That makes sense now. So 14 and 14. So what I've got here then is this line. And as we just said, right, let's just simplify here. Okay. So I've got 1 lot of 14 plus 2 lots of 14. So that's 3 lots of 14 here. So 1 is equal to 3 lots of 14 minus then 1 lot of 41. Perfect. And once we obtain this here then, we've finished the question, right? Once we obtain something of this form here, so 41 times A plus 14 times B is equal to 1. Perfect. We've completed the question. Okay. So the only thing left to do here then is just identify A and B. So in that case then A here, so A is the coefficient of 41 here. In that case, A is equal to minus 1. And B then is equal to 3, right? That's the coefficient of 14 here. Okay, so B is equal to 3. And there we have it. So question complete. And that gives us the solution to part B. As we just said, right, the solution to the full question. Apologies again for the slight mistake here. It was just a tiny error, but hopefully that didn't cause any confusion there. So there we have it then, right? That gives the solution to the one practice question for this video here. And that brings the end then of this video here on Bezout's identity.